Hello again, grade 7s. In today's lesson, we are going to talk about multiple changes of state or phase changes between our three primary states of matter. And we're also going to talk about a complicated property of a substance that is referred to as the specific heat capacity. Learning outcome is to explain changes of state using the particle model of matter. Let's start off with this difficult concept of specific heat capacity. Specific heat capacity, which has a very wordy definition, is the amount of energy required to change the temperature of 1 gram of substance by 1 degree Celsius. Okay, let's look at an example of this. We're going to use ice and water as my example. Okay, let's say that here's a block of ice, and I'll say we just have 1 gram of that. And maybe right now this block of ice is at a temperature of, I don't know, negative 10 degrees Celsius. What I want to do is I want to increase the temperature of this 1 gram block of ice by 1 degree Celsius. So if I have that same 1 gram block of ice, and if I increase the temperature by 1 degree Celsius, it'd be just slightly less negative at negative 9 degrees Celsius. What specific heat capacity is it tells you how much energy would be required to do this. How much energy would be required to take 1 gram of ice and increase its temperature. So by increasing the temperature, it would be going up by positive 1 degree Celsius. And then we go up by 1 degree Celsius. The amount of energy to do this with ice would be 2.00 joules. So I need 2.00 joules of energy to take 1 gram of ice and increase its temperature by 1 degree Celsius. Well, let's look at water. Let's say I have like a beaker of water. I'll draw 2 beakers here. And then let's just get a different ink color for the water. So let's say we have my water here. And let's pretend like I have 1 gram of water in this beaker. Obviously, you'd have probably a lot more than 1 gram. And let's say that this beaker of water is at a temperature of 10 degrees Celsius. So it's pretty cold. And what I want to do is I want to take that 1 gram of water and I want to increase its temperature by 1 degree Celsius. So to increase it by 1 degree Celsius, we'd be going up to 11 degrees Celsius. So now we're up to here. The specific heat capacity would tell me how much energy is required to do this, to take 1 gram of substance and increase its temperature by 1 degree Celsius. And for water, I need more energy than ice. So I would need 4.19 joules of energy to change the temperature of 1 gram of water by 1 degree Celsius. The way we're going to interpret this is by identifying what does specific heat capacity mean in terms of how difficult it is to change the temperature of a substance. And it turns out that the higher the specific heat capacity of a substance, the more difficult it is to change its temperature. So if we look at our 2 examples, we have ice at 2.00, and it has really funky units, joules divided by grams times degrees Celsius. And we have water, which has a higher specific heat capacity. It would be a lot more difficult to change the temperature of water in comparison to the temperature of ice. Why? Because you have to put more energy into doing it. Maybe one analogy I could use is if you've ever been to like a video arcade, assuming they even exist anymore, but I think there's a few of them that can be attached to some movie theaters. You may have walked around there, and the different arcade machines require tokens or coins or points to play. And some of those games require more tokens to play than other ones. So we could think of, like, for example, water as being like a machine that requires a lot of tokens to play. and ice as being a machine that requires less tokens to play. So in terms of like looking at the actual analogy, going back to like the temperature, it's more difficult, or it requires more energy to change the temperature of water, just like it would require more tokens in an arcade to play a game that maybe is a little more advanced than something like really, really simple. I don't know if that analogy works for you or not, but it's one way to kind of think about it. So the higher the specific heat capacity of a substance, the more difficult it is to change its temperature. And it turns out water has a high specific heat capacity. This might be very hard to believe because it's not very it doesn't seem difficult to boil water. If you take water and you put it in a pot and heat it up on the stove, it takes maybe about like 5 minutes for it to boil, depending on what temperature setting you put it at. But in comparison to other substances, water actually does take quite a bit longer for its temperature to change. And let's look at another example of this. I'm just going to erase this. So the question I have here is that, let's say it's like in the middle of summer where it's really, really warm. It turns out in the middle of summer, if you were like at like some kind of lake resort, and let's say you went into the water at midnight and compared to the water at sunrise, it turns out that if you went into the water at midnight, it likely would be a lot warmer than it would be at sunrise, which seems to be a contradiction because at midnight, there's no sunlight. So you think, okay, with less sunlight, then the water would be cooler. And at sunrise, you do have sunlight, yet the water's colder. Well, here's a reason why. So let's do a little illustration again. Okay, so let's say that here's my lake, and we're going to look at sunrise. Maybe at sunrise, my temperature of the water is like 5 degrees Celsius. And then we have sunrise occurs. When sunrise occurs, then we start to have rays of light that shine onto the water, and it starts to warm it up. But the problem is, because water has such a high specific heat capacity, it takes a long time for this to happen. In fact, it takes probably until about, like maybe noon for like the water temperature to get to something that's like comfortable, maybe like getting into the range of being like 10 to 15 degrees Celsius. And again, the reason it takes time for this to happen is because of water's high specific heat capacity. Now, at nighttime, well, kind of like the reverse thing happens. So at nighttime, so let's draw my lake again. At nighttime, water has had all day to absorb that energy. So maybe it's at a temperature of like 15 degrees Celsius. Now, once the sun goes out, that water is going to start to lose some of its energy to the surrounding air. However, once again, it takes a while for that to happen. It takes a while for water to give up whatever energy it's actually absorbed. So by the time it's midnight, it still has a bunch of that energy that's taken in during the day. So it is a very important characteristic of water. It has a high specific heat capacity, which means that it's difficult to change its temperature. Now let's look at changes of state or phase changes. When I say changes of state or phase changes, we're going to look at different terms that can be used to describe when, for example, a material goes from being a solid to a liquid, or a liquid to a gas. And there's all sorts of combinations. In fact, there's 6 of them we're going to look at. So let's start off with fusion. Fusion is the change of state of a substance when it goes from a solid to a liquid. The easiest example of this would be you just simply take an ice cube out of an ice tray, you put it on the counter, and then it melts. The less scientific name for this would just be melting. Way I always memorize this term is I think of fusion as, I don't know if they make this chocolate bar anymore, but there used to be a chocolate bar called Fusion. And you can think of the chocolate bar like initially as being solid. And then when you put it into your mouth to eat it, it melts. And then it turns, I suppose, kind of into a liquid, if you want to think of it in that way. 2, we have solidification. Solidification involves the change of state of a substance from a liquid to a solid. So we're going in the reverse direction now. One example of this would be the reverse process. Let's say you had an ice tray and you just put some liquid water in it and then you put it into your freezer. Well, eventually the liquid water would turn into the ice cubes. Or, you could also take a can of pop and put it into the freezer for I wouldn't do it for very long, because once again, the problem with water is that when it does turn from a liquid to a solid, it actually expands. And if it expands, that water that's in the pop expands, it can actually cause the pop can to explode. The more common term for solidification would just be the freezing of a substance, going from a liquid to a solid. We also have vaporization. Vaporization is the change of state of a substance from a liquid to a gas. Easiest example of this would be you take some water, you put it in a pot, you put it on the stove, and then you heat the water up, and then eventually it reaches its boiling temperature where the water is going from a liquid into the steam, which is a gas, and that's what we call vaporization. Although, again, I think the more common term for this is, we speak of water anyways, like if it's a day where it's rained out and you have water all over the street, and then the next day it's quite sunny, well, that water disappears because it's turning from a liquid, which we can see, into a gas, and the gaseous water vapor we cannot see. We can't see it because there's a lot more space between the particles, and if there's a lot more space between the particles, it's more difficult to see. Kind of think about that analogy I used with the sand before. If you have a bunch of particles of sand and they're very close to each other, you can see the clump. But as you start to spread these particles of sand out, it's very, very hard to see them individually. Or, as we're going to start to get into the ones that are a bit more complicated, we have condensation. Condensation is the change of state of a substance from a gas to a liquid. The example I'm going to use for this one is, say it's a really, really hot day and you have a glass of lemonade, a very cold glass of lemonade, and you bring it outside. And then maybe after about half an hour, you notice that on the outside of the glass, you're getting these little tiny droplets of water. Well, here's what's happening in this situation. Okay, so you have your glass, and we'll just draw the lemonade with a different color. I'll just do blue. Okay, so what's happening in this situation? So I have, again, my glass with the lemonade inside of it, and you start to notice these little tiny droplets that begin to form on top of the glass. Well, what's happening is on the outside of the glass, you have water vapor. Water vapor is water, and it's in a gas state. What we know is that our direction of thermal energy transfer or heat transfer is always from an area where it's hot to where it's cold. So what happens is this particle or this molecule of water vapor would transfer some of its energy from the hot air into the cold glass. When it transfers some of its energy into that cold glass, well, it loses energy. And when it loses energy, what would happen is the water vapor would actually turn into a liquid. So you start to get these little tiny droplets that form on the side of the cup. Okay, let's erase that. We also have something called sublimation. Sublimation can be one of the following two phase changes. It can be the change of state from a solid to a liquid. So in this case, we're skipping the liquid state. We're going directly from a solid all the way to a gas. Change of state from a solid to a gas. An example of this is, you may have heard of dry ice. Basically, dry ice, I believe it's made up of solid carbon dioxide. So let's take another beaker. And let's say inside this beaker, you have a chunk of dry ice. That chunk of dry ice is carbon dioxide in this solid form. And then you pour a bunch of water into it. Okay, pour a bunch of water into the actual beaker. What happens is instead of it melting into a liquid, it actually just, the dry ice directly turns into, I don't want to say steam, it almost turns into like a fog. So as a result of pouring water onto the solid dry ice, the dry ice then turns into this fog that you can see. And this fog would be a gas. So you're skipping the liquid phase change and just going directly from a solid to a gas. And that's called sublimation. Sublimation can also be the reverse phase change. It can also be the change of state from a gas to a solid. An example of this would be frost that is forming on a windshield. Okay, so let's look at an example, or let's try to explain like why this happens. Okay, so let's say this is the windshield on your car, and we'll say this is the inside of the car. Okay, so the inside of the car, let's say you drove home at night, you parked the car, and then when you're driving home, you have the heat on. So the inside of the car would be warm. And you park your car on the side of the road. And then, obviously, if it's like a cold, really, really cold winter day, the outside of the car would be cold. So what you have is, once again, just on the outside of the car, you'd have some water vapor molecules. Again, water vapor means it's in a gaseous form. Now, initially, because they're in contact with the windshield and the windshield is warm, they're going to be in this gas state. But as you go through the night, again, heat always transfers from hot to cold. So you have the direction of energy transfer going this way. So what happened is these water molecules on the outside of the car, they would start to lose energy because that energy is being transferred to the outside air molecules. And when they lose energy, the particles in the material start to come closer together. And this happens very, very rapidly to the point where the water vapor actually just goes directly into forming a layer of frost. So that's another example of sublimation. All right, that's it for this assignment. Sorry, not for the assignment. This is it for the lesson. The assignment you can complete is called Learn the Lingo, which deals with just being familiar with the different terms involving the phase changes, and also being able to look at examples of phase changes and then properly labeling them. And I will talk to you in the next lesson when we talk about methods of energy transfer.